Hello, for today's video lecture we're going to be talking about the impulse momentum theorem for a rigid body. So the impulse momentum theorem states that the impulse exerted on a body will be equal to the change in momentum of that body. So this applies to both the linear and angular versions of these terms. So for the linear version we've got J equals mv final minus mv initial. That is, the linear impulse is equal to the final momentum minus the initial momentum. And this is what we talked about with particles. So with rigid body systems, we also have to worry about angular impulse and momentum. And this is summed up in the equation K equals I omega final minus I omega initial. So this is the angular impulse, the final angular momentum, and the initial angular momentum in our system. So we have both of these terms at play, and both of these equations need to be satisfied in any system. So when working with fixed axis rotation, we're just going to use the rotational impulse momentum equation, similar to how when we had fixed axis rotation we just worked with m equals I alpha in previous chapters. So we're balancing the impulse with the change in momentum. K equals I omega final minus I omega initial. And an example of this would be the motor turning in this case, a miter saw blade. So I might worry about the initial and final angular momentum of the blade, and possibly motor over armature here, and the angular impulse exerted by the motor itself. So for this equation, we need to be sure one thing is consistent though, and that's we need to take all moments and mass moments of inertia about the same point. So if we are taking I about the center of gravity, our moments need to be about the center of gravity. If we're taking I about the axis of rotation for our fixed axis rotation system, we need to take the moments in K about the same point. So as long as you're consistent, this equation should work with this. Now moving into general planar motion with the impulse momentum equation. So this is where we both are translating and rotating in two dimensions. We can use both the translational impulse momentum equations and the rotational. So for this, we're going to break it up into x and y components because we've potentially got x and y motion in our 2D system. And the rotational impulse is just one equation. This is because we are going to be rotating about the z-axis, and we are going to have just that single direction. So if we jump into 3 dimensions, we would have x, y, and z for our linear impulse, and we'd have x, y, and z for our rotational impulse for that. In these cases, it's important to use the velocity of the center of mass of the body. So when we're talking about v final, v initial, x, y, etc., all of those need to be the velocity of center of mass. When you take the moments and mass moments of inertia about the center of mass of the body. So all of this refers to the center of mass as our point of interest when we're examining these equations. So if you do that, these equations should work out just fine. Again, rigid bodies, the velocity of the body is going to depend on the point you're looking at. So we need to be careful where we are taking that about. All right, so how do we solve these problems? So just as we did with the particle systems, the first step in solving the problem is to set up a diagram showing the initial and final states, as well as any forces or moments causing an impulse between those two states. So here I've got an object is kind of rolling along a surface. So there is some sliding happening, which is going to cause some friction. And so I can see that the velocity of the object is going down, but the angular velocity is going up. This friction force is going to be causing both a linear impulse over whatever time that is happening for, and it's also going to cause a moment because this force is not acting through the center of mass. So forces can cause both linear and angular impulses if they are not acting on the center of gravity here. So step 1, set up your diagram. Step 2 is to put the values into your equation. So add any known values and determine what your unknown values are. If the problem is 2 or more dimensions, you're going to need to break the linear equations like we talked about into x and y components. And then the angular impulse is going to remain a single equation here. It's understood it's about the z-axis when we're working in 2D here. So we've got up to 3 equations. We can solve for up to 3 unknowns. Make sure you have enough of those. So last step is to solve your equations for any unknowns. Again, make sure you have at least as many equations as you have unknowns. If you don't have, or if you have too many unknowns, you might need to relate linear and angular velocities with kinematics. So oftentimes, if it is something like rolling with slipping, we can relate the linear velocity to the angular velocity of something that's rolling without slipping. The equation should not be too complicated, but just as with any of these problems, use an equation solver if you deem that necessary. All right, so one add-on topic for this is the conservation of angular momentum. So we can see that in instances where there's no external moment, and thus no external angular impulse on a body, then the angular momentum would remain unchanged. So k, which in this case is going to be equal 0, is going to be equal 1 omega final minus I omega initial. So the final momentum must be equal to the initial momentum in this case. So this is known as conservation of angular momentum. And similar to linear momentum, it has its use cases in certain circumstances. So the first one, it's useful when a body changes shape and thus its mass moment of inertia. In a lot of cases, and so the example that's usually given for this is like figure skaters. So if a figure skater is skating along and they start spinning, if they pull their arms in, they're going to reduce their mass moment of inertia, and so that I value changes. And so they're going to increase their angular velocity because the angular momentum as a whole needs to stay constant. So if you decrease I, you're going to increase your omega value in the final state. So that's one instance where it's going to be useful. The other instance is in the analysis of rigid body collisions. So I'm not going to go too much into detail there, but the conservation of angular momentum will be conserved usually about the point of impact in a rigid body collision, and we can use that as one of our equations to relate the initial and final states in that collision. All right, so that's all we have for today's video lecture. Thank you for watching, and I hope to see you again.